So just before the break, I showed you we in our design, you will see shortly that we will need a value called gamma, and gamma is a ratio between h prime to h, and simply it tells you the lever arm, because if the h prime is so small compared to the h, it means we're losing lever arm. Okay, you can find it manually using this very simple calculation by knowing the concrete dimension, by knowing the cover, the tie diameter, and the bar diameter as well. We can find the gamma, or the code provides a nice table that gives you the gamma directly. As I said, I make a PDF. I have a PDF available on my D2L that has all the design tables that you will need in this column. Please make sure you download them today. Okay. Uh, Now, one more thing that it affects our design, which is the rebar layout. The rebar layout. So we have two rebar layout. One is by adding the rebar on two opposite faces, and the other one is by adding rebar all around the column. I would say this one here is the most common one. And if you wonder why, because simply this one here, it looks like a beam, and this one is more like a column. And typically our columns will have more axial force with little bending moment, and that's why we need to reinforce our column as a column, not as a beam. Okay, so please take a note that in our class or our design, we will follow this one on the left here. We'll place a box around this one here, which means we will place the rebar on all the sides of our column. Now, here is our first numerical example. I'm going to spend some time to go through the example, and then we'll show you how do we design a column. So you can tell here there are some inputs. The axial force is 2,500, and just to make it clear, in this example, I didn't bother myself to show you how do we find the axial force. On Monday, I'm going to show you how do we do a load take down and see what should be the axial force on a column of a building. But in this example, because that's not my scope right now, I give you already the B factor. On Monday, I will teach you how do we find the B factor. Same as I did for the beam, if you remember, at this point of time, again, my focus is to show you how to design the column, not how to find the loads on the column. So the loads are available here, given to you directly. So the PF is available, the moment F is available. Or you have the K multiplied by L unsupported, 4 meters, and then the F prime C is 40 MPa. The F field, as usual, is 400. And one more information that you will need is the cover is 40 millimeter, and the M1 divided by M2 is plus 0.5, plus 0.5. And so you can see, single curvature, it is plus. If this is double curvature, it means this will be minus something. Okay? Now, let's see how do we design a column. And I promise you, this initially will look like crazy like hell, but I can tell you the easiest design in the whole course is column design. Okay? It just any chart, as long as you know how to use the chart, then the column design is very, very easy. Now, how you do that is by simply by assuming the reinforcement ratio, and it is an assumption for now. It's nothing firm, nothing firm. It's just an assumption. We always start from the minimum. So the minimum reinforcement ratio, as we discussed before, is 1%. And also, if you remember, the column should have anywhere between 1% to 8%. And practically, we don't do 8, we do 4 because of the splice and the overlap. So we always start from the minimum. Minimum percentage of reinforcement is 1% in a column. Once we know the reinforcement ratio, we can, and the axial force, we can use this design aid. Okay, so where can you find the design aid? Any help? Where can you find this design aid?
D2L.
D2L. Okay, one more time, it's available here. So I'm gonna scroll up and to show you what's available on D2L. Okay, so there are so many charts available here. Now I want to teach you a little bit about how do we pick one specific chart. Please, I'm gonna zoom in so you guys can see better. Forget about how to use the chart for now. The question right now, which one should I choose? Now let me ask you, what do you think about this chart? What characterizes this chart? You can see here, really this is for F prime C 25 MBA, and F field is 400, and this chart is for 25 and 500. What do you think? Can I use this one, or I should be looking for another one? What do you think?
No, you can't use that. We're not using that.
Exactly. So look at this. We scroll down. Let's see. What do you think here? What
Yeah,
do you
that we
think?
can use. The
Let
No.
me check the
400 one we can use.
let's check the problem. Let's check the problem. The problem is here. The problem is here. The F prime C is equal to 40, which means this is not the chart. Let's scroll down until we see a 40. So here we go. So you can see this page here on 7.1.4. We have 2 of 40. Let me ask you, we choose the one on the right or the one on the left?
The one on the left.
Down on the left. Why? Because the F prime C is 40 and F field is 400. Okay, so please choose the right one, not any one. You must make sure you have the right F prime C and F field. Now it's time to show you how do we use the chart and what this chart does for us. Okay, I'll show you what does it do for us. Now let's go back to our example. Here is our example. And you can see here, if I zoom to the top, you can see the 40 and 400. So I'm using the one on the left. And how we use the chart, very, very simple. I'm going to show you first what's on the y-axis. So the y-axis is your PF or PR maximum in mega Newton. So those numbers, like let's say 1 and 2 and 3 and 4 and 5, this is the axial load factor affecting your column. How much that number in our example? Anybody remembers how much was the axial, the BF?
2,500.
2,500. Okay, I think I made a mistake. Because 2,500, I'm going to write it here. 2,500 kilo Newton. This equals to 2.5 mega Newton. Okay, so the number must be in mega, but I made a mistake, but I don't think the mistake will make any difference. So we're supposed to go on this chart with this arrow here. So at 2.5, you're supposed to go horizontal. And what happens here? What happens here is we have here the x-axis row. And as I said, what we do is we start with the minimum reinforcement ratio 1%. And simply, if we take the axial load and the reinforcement ratio, what they do is they will create for me a point on one of these curves. We have so many of them. We have one curve, another curve, and so on. So all those are different curves. They give you the size of your column. Okay, so you can see I made kind of a little bit mistake and I use 3 mega Newton instead of 2.5, but I don't think will change our results, and I'll tell you how. Okay, so again, you can see if I zoom in, looks like it intersect here somewhere in between 350 by 350 and 400 by 400. Okay, I'm asking you, do we build our column 375 by 375?
No, why don't we
No.
just build 400 by 400?
We said before, when it comes to the practical guide of our design, it's always multiple of 2 inches, 50 millimeter. And that's why even the column is in between 2, then we take the maximum, and you can tell here my column dimension is 400 by 400, and the area is 0.16 meter square. Now, you can use this table. So, I mean, let me ask you. So obviously from what I did, what does this chart do for me? It finds what for us?
Gives you your AG, your area of steel, or area, gross area.
Gross area. I mean, I would say it gives you the concrete dimension of your column. Would you agree?
Yes.
That
Okay, so let me be specific. Look at this. So in our class here, we're not gonna really take a crazy shape of our column. Our column can be rectangle or square, or it can be circular. Okay, there is no other crazy shape in this class. Only circular, rectangular, or square. If your column is a square, can you tell me right now what should be the dimension? So let's do it, huh? For the same numbers, huh? You can tell that this should be a 400 by 400. Would you agree? If my column is a square, look at the chart, it tells you 400 by 400. Okay?
Yes.
Okay, how about if my column is rectangular and simply my architect said, you know what, make this guy 250, so we can incorporate this inside our wall, because otherwise it will look ugly. Huh? If your column extrudes outside your wall, it will look ugly. And so if the architect tells you use this dimension as 250, can we find the other dimension? And how?
Would it just be 550?
You have to look at the table.
No, it will be 0.16. That's the area divided by 0.25, which is your the width of your column. So look at this. I'm gonna zoom in to see. So this chart is telling you if your column is a square, it's 400 by 400. If your column is not square, then this will be the area gross. Now I know that my column, the area gross, it's supposed to be 0.16. And if I divide the area by the width of my column, I will get the length of my column. Are you following?
Yeah, I'm following now.
Okay.
And if the length of the column is not a multiple of 50 millimeter, then you must round it. Let's do, please. Can I get somebody to help me? 0.16 divided 0.25. I need some help, please.
0.64.
0.64. Nobody builds 0.64. That's so this is 600. So it will be a 650. Yeah. So this dimension here will be 650 millimeters. So your column will be. I can simply replace this one here by 650, and my column will be 250 by 650. Now, finally, what if my column is circular? What do I know about this circle here? All I know is the area is equal to 0.16. Is anybody good at math to tell me what is the diameter of your column?
Okay.
We
0.16 divided by pi.
let me write it for you guys. The area of a circle is equal to pi multiplied by d squared divided by 4. Okay? This is the area of a circle based on the diameter. So from this one, what we know that this number is how much? We know this guy is equal to 0.16 meters square. Can we find the diameter? Of course. We have to multiply. I need some help, please. Somebody to multiply 0.16 multiply by 4 divided by pi, and then get the square root and tell me what should be the diameter.
0.45.
So D is equal to 0.45.
Yeah.
Yes.
Okay, so this will be so 450 mil, huh? So D will be a 450 mil. Remember the units, huh? So this number is a meter square, and I said 0.45, but then the diameter I put it here in millimeter. So again, by now you're supposed to know what happens. Number one, the job of this chart here after choosing the right chart is to tell you what should be the initial column dimension you should start with. Very simple. If it's a square, you get the number from the chart. If it's not square, then use your math to find the diameter, if it's a circular, or if it's a rectangle, I must give you one dimension. Let's say 250. The architect will give you one dimension, and it's up to you to find the other dimension. Is that clear? Should I proceed?
But if that is the case, you always give area, right? You always
As I said, look at the
give
chart. Look
area.
at the chart. Look at the chart, please. If your column is a square, so here we go. This will be the dimension of your square.
Yeah, I
If
got
your
it.
column is not square, please use the area here to find the other dimensions. Now, once you know the dimensions, what you have to do, and please don't forget, number one is to make sure that your column is a short column. Because I'm going to make it clear, if your column is not a short column, let me ask you, do we design the column for only 200, or we have to take the moment that comes from the buckling? I'm going to say my question one more time. If my column is a cylinder column, do we design our column for 200 only, or we also have to consider the moment due to the buckling?
You have to design also the moment due to the buckling if it is a cylinder.
Yes, so that's why I'm doing here. You will see here, as soon as I get one dimension for the column, remember, that's not a final. This number here is not final dimension. This is just an initial estimate. It can be right or can be wrong. So I'm using right now 400 by 400. And what I will do is I will simply do the check. I will go ahead and check this condition here. Okay? If this condition is happening, what does it mean? It means short column. If this condition is not happening, it means cylinder column. And I told you the fix. If it's cylinder column, then we have to bump up the dimension of our column. Let's do it. So in the example, this number is given, KL unsupported, which equal to 4,000 millimeter. And the radius of gyration, we said this already, is equal to 0.3 times 400. Not the square root of I divided by A. Remember, huh? In concrete, the radius of gyration, if we have a square, so it's 30% of the dimension of the column. If it's a circular, then it's a 25% of the diameter. So guess what here? We got 33. Done. So let's leave this number. And then what we do is we go to the other term, which is 25 minus 10 multiplied by M1 divided M2. And this number is given to you. Okay? And then divided by square root of BF. So BF, this is my BF, which is 2,500 kilonewton. And this one is F prime C. And this is the area gross, which is 400 by 400. The only trick, I'm going to box it out for you. This is the only trick. Why this is tricky? Because of the units. The 2,500 is a kilonewton, while everything in this equation is in millimeter. Then what I did is I simply multiply by Newton by 1,000 to turn my kilo Newton into Newton. And what happens here, look at this, is equal to 32. You can check, please. I would please recommend you to do that right now. I'll give you 2 minutes, please, because it's very important for you. One of the things I can see in my students, some of you, because maybe the equation is not clear, or maybe the math on my slide is not clear, they don't do the math right. They miss some bracket. And so please ensure right now, you do it right now, make sure you understand the formulation, which is here. Please use this one here. Please do 25 minus 10 multiplied by 0.5 divided by, this is everything here is under the square root, which is not really matching here. So you can consider, you can continue the square root here to the end. Same one here. Take the square root here to everything. I want everyone to do it and make sure you get 32. Any good news?
I did something wrong. I got 39.2.
No, sir, it has to be 32. So basically it's 15 over a square root of 15. So the whole this term here on the top, it's 15. And just do the square root of this one of this term here.
After the 25 times 10 to the third, after that bracket, is that a division sign?
All are division. So look, I mean, please forget about this one. Do this, do this. This is even clear.
I got 32. Looks good.
Okay. Please, everyone in the class, do that. I have a problem with some of you that cannot do the math right. Okay. Now, once you get the 32, then you can tell. Let me ask you, the column, the lambda for the column is 33, while the maximum lambda is 32. Is that a short column or a cylinder column?
Cylinder column.
It's a cylinder column because your lambda, so the lambda for the column exceeds the lambda maximum. Please think about this number here as your limit, the lambda maximum. Okay, so that's why I said here what you have to do is, please, how I solve this one, try next size. So we started from 400 by 400, and I'm saying try to see if it's going to work or no. So I'm using here 450 by 450. I will re-estimate the whole thing again, which is not very difficult. I'm going to go ahead. Actually, there is a mistake here. Please take a note. Please take a note that this number is 4. So the length of the column doesn't change. However, the dimension of the column already has changed. So don't use the old dimension. Use the new dimension 450. And again, we're on the safe side because I bet you if you use 450 instead of 400, for sure this number will be less than 29.7. Can I get the right number, please?
Uh, 29.63.
Okay, so it looks like the number is right. I'm not going to say that this is the problem. The only thing is, please correct this on your slide and take a note that this is 450. We're dividing by the new dimension that I picked. Okay, and I'm going to do the condition one more time. So the condition, everything is the same except this part here, which is the area gross right now is 450 by 450 instead of 400 by 400. And what happened here? The lambda maximum is 36 and the lambda for your column is 29.7. Do we have a short column? Is the 450 by 450 is a short column?
Yes, it is.
Yes, yes. And that's why, because it's short column, then we can use whatever Tahir teaches us to design our short column. Now we know it's a short column, and I'm going to stop here a little bit because I'm going to stop here. I'm going to show you how do we simply design our column. Let's look at this picture here. Okay, so what I'm doing right now is I'm opening another PDF that's available already on the D2L. And so what do we call this guy? And I gave you kind of introduction about this, last class. Some is called interaction diagram. Interaction diagram, which is simply the interaction diagram is a curve that represents the relationship between the moment and the axial force that can be supported by a given concrete section. Okay, we will use the interaction diagram to design our concrete column. Again, please don't get overwhelmed by the shape. The use of those diagrams are very simple. Just take it easy and follow me. Now, before I continue, I wanna just point out something that may be surprising for you. We do not have a single interaction diagram rather than have a 76. We have total of 76 interaction diagrams. You know what? Just for information, I'm going to scroll down to show you that we have many of them. Many of them. Really, what's important at this point is you need to understand why do we have many of them, not only one. Why do we have many of those interaction diagram? Because every interaction diagram is based on some assumptions and some parameters. Please watch the following. So I'm going to point out here. I think it's protected, so I cannot write on it. But please look at this. What is the value of the gamma for this diagram?
0.6.
And what is the value of F prime C?
25.
25.
25. And what is the shape of the bars? The bars are on opposite side or all around?
All around.
Okay, wonderful. Please watch this. I'm going to scroll down to the next one. What it changes between the previous one and this one? What has it changed?
The value of your gamma.
Gamma. So you can tell, this one is used for gamma is equal to 0.6 and this one is for 0.7. But still, the 25 is the same and the shape of the rebar is the same. Let me scroll down a little bit further so you can see here there is one for 0.8, there is one for 0.9, and for sure there is one. The gamma cannot be 1, Let's be clear. Can the gamma be 1?
No.
Why is that? Can you tell me why gamma cannot be 1? Never?
Because h prime over h. So if it's that is the ratio. So if it's 1, then there is no h prime.
No, it means your rebar is outside your concrete box because h is equal to h prime, correct? And if h is equal to h prime,
Yeah.
it means you placed half of the bar outside your concrete. As simple as that. Anyway, that's for fun only. But gamma is less than 1 all the time. We have several, I think it goes from 0.6 to 0.9 with a step of 0.1. Now, let's see here. What changes here?
MPa. Compressive concrete strength.
Yeah, the changes here, it's F prime C. And the gammas also, one more time, we repeat the same thing. We do one chart for gamma equal to 0.6 and 0.7 and 0.8 and 0.9. And again, look at this. What changes here?
F prime C.
35, So 35, and we have 4 of them. And then we have 40, and we have 4 of them. Different value for gamma. And then we have what? We have 45, I guess. We have 45, 4 of them. Like gamma is equal to 0.6 and 0.7 and 0.8 and 0.9. What else? We have here. So let me ask you here. What change? What's difference here? Do you see a difference?
It's a rectangle two-face rebar.
Two faces. So the rebar layout here, this chart is designed where the rebar is available only in 2 opposite face, but not on this face, on this face. And that's why you can see we have more of those, okay, now let's go to, again, I'm not going to spend more time on that. You get the idea. We have so many of them because there are some parameters that will simply change from one chart to another chart. And I'm going to show you what exactly are those. However, if you scroll down a little bit further, you will see we have some chart for, we're very close. We have chart 4,
Circle.
circular column. So please note the following. Here is what I want you to know. And before, not after, before you start working on the interaction diagram, there are few things you have to decide and make sure it's clear. Number one, the shape of my column. The shape of my column is a square or circular. That's number one. Number two is, what is the rebar layout? Is it on all the faces or on only two opposite faces? Number three, what is the gamma value? Is it 0.6 or 0.7 or 0.8 or 0.9? Number four is the F prime C. Are you following? Four things you have to decide before you even say, here is this interaction diagram that I'm going to use. Let's say it one more time. Number one, the shape of my cross section. Number two, the rebar layout. Number three is the value of the gamma. Number four is the F prime C. And that's why, please look at my screen. What you will see is, you will see I'm trying to find the value of the gamma. The value of the gamma, and with the value of the gamma, you must make some assumption. For example, like, what is my bar diameter? And we said in our class here that my bar diameter is minimum 20, and that's what I'm doing right now. I assume that I'm using 20 m bars, and I'm gonna remind you, if I have 20 m bars, and I have 450, same diagram. Now watch this, please. So the same chart here, I can go 450. So this is my line here, and I'm using 20 m. So you can tell how much. Can anybody tell me how much is my gamma?
0.73.
Okay, and what happened is, here you can do it from the table or you can do it manually, but I would say the table will save you a few seconds. So let's go here. Now we can tell, I got the same number. I got the same number. Gamma is equal to 0.73. Okay, great. Now some of you will say, Tahir, wait. So there is no chart whatsoever in the available chart that represents gamma is equal to 0.73. What should I do? Here is the simple answer, and I'm not going to go deeper because this will take, if I am in class, I typically spend 15 minutes to discuss with my students. Okay, so please round down. So 0.73 is in between 0.7 and 0.8. Please round down. So use gamma is equal to gamma equal to 0.7. Does it make it simple for you without any deeper details? Gamma round down to 0.7. Don't use 0.8 because 0.7, it's more conservative, because 0.8, it assumes that we have a larger lever arm, while in fact we have less lever arm. If you want to get idea why I chose 0.7, not 0.8, choose the smallest 0.7. Now, once you know that it's 0.7 and the concrete is simply 40 MPa, let's go back to the interaction diagram and let's scroll down and see which one should we use. I'll go to the top. Okay, I'm asking you, can I use this one? Please say or no.
No.
No. Okay, so I'm asking you, this one is gamma is 0.7. Can I use this one?
No.
No, because the F prime C is 25. So anyway, for the sake of time, I'll scroll down until I find the right one. So 30, 35, and then finally, here is our 40, and then we have 7. So here we go. Now we know that we're going to use this one. Why? Please understand. Number one, gamma is 0.7. F prime C is 40. The shape is a square or rectangle, it doesn't matter. And that we have bars all around. Okay, now we know we're going to use this one, but the question is, how can we use it? I know the shape of the interaction diagram, it looks scary, but I'm going to show you how easy it is, easy to use. Please, before I do that, I want you to understand the numbers on the screen. So on the y-axis, on the y, I'm going to zoom in. What is on the y? Very simple. It is your PF or BR divided by area gross. So what you have to do is you need to prepare this number. You need to divide the PR or the BF divided by the gross area. How about on the X? What is on the X? It is the MR or MF divided by area gross multiplied by H. We have to prepare those two numbers to enter our interaction diagram. Where it's over there. Let's go back to our sheet here, so you can see I'm dividing my BF divided by 450 by 450. I got 12.34 MBA. The only tricky part is the units. Pay attention to the units where I multiply here by 1,000. Why by 1,000? Because the number in the chart should be MBA per millimeter square, while the dimension of the column is in millimeter and the force in kilonewton. So I'm trying to turn my PF into Newton. So I got 12.34. Same thing I go here. I'm dividing my MF divided by area gross by H. So 200 divided by 450, which is area gross. So this guy is the area gross. And multiply by the H, which is 450 again. Again, the tricky part is you must multiply times 10 to the power 6 to turn your moment from kilonewton meter into Newton millimeter. And we get 2.19. Now, what is next is over there. So I'm not going to go to the interaction diagram on the chart here because I already copied to my my slides here. So now you have two numbers, 12.35 on the vertical and then 2.19 on the horizontal. What you do is, this is a pair of coordinates. Huh? Think about those numbers, like this number here, and this number here as a pair of coordinates. This one here is your X, and this one is your Y. I will write it down. So think about it as a point that no coordinate, 2.19, comma, and that's the X, 12.34, and that's the Y. What you do is you need to represent this point on your interaction diagram. How? Very simple. I go here 2.2, almost 2.19. I go vertical. I go here 12.35. And then finally, I got my point here in my interaction diagram. Okay, now I'm going to show you how easy. Now, every one of those lines, like you have a curve, huh? So you have one curve here, another curve here, a third curve here. Every one of these curves represents a different reinforcement ratio. Okay, so if your point is here, it means we need less than like 1% reinforcement ratio. What if I block my point and my point it came on the 2, like here? What do you think? How much reinforcement I need?
2%.
2%. How about if my point comes here? How much reinforcement do I need?
3%.
Okay, how about if I get my point here in between, exactly halfway in between 1 and 2?
1.5.
1.5%. Really, the closing remark is, I already marked it on my slide, that by code, we cannot add less than 1% of our reinforcement, not less than 1%, which means if my point is within this area here, it means I must bump up the reinforcement. Don't tell me I'm going to add 0.7 or 0.8. We need to add 1%. Are you following?
Yep.
So it's as simple as, listen, as soon as you say, okay, you know what? I know which interaction diagram, you have to prepare two numbers. Number one is PF divided by area gross and take care of the units. You find your first number, and then you divide MF by area gross by H, then you get another number. And this will create a point on the interaction diagram that you have chosen, the right one. And simply from the interaction diagram, what do we get is, we get our reinforcement ratio minimum 1%. Now, if we know that our reinforcement ratio is 1%, what do you think? What will be next? You simply have to go ahead. You know the reinforcement ratio. You multiply 1% that you got from the interaction diagram times area gross, and this will give you the area of the steel. Okay, so here we have a 2025 millimeter square, and as I said, minimum we use 20 m. We can use 10 m. We cannot use 15 m for vertical bars, and we use 20M. And we know by now that every 20M is a 300 mil, and that's why I need 8 bars. I know some of you will say, no, wait, we need only 7. Can we place 7 bars on our column?
No.
Why no, Jelly? Why?
Well, you can use you can play 7, but in balance because the other side has no bars.
Exactly. So the point is, as Jelly said, here is the rule. The rule: your column must be symmetric. Your column must be symmetric, which means 7 doesn't work. It means it has to be 8 bars. Okay, are you following?
Yep.
Okay, so once you place your 8 bars in your column, we have to do a few checks. What are those few checks? Number one, we must ensure that this distance here is a little bit, it can allow for the flow of concrete. And that's what I'm doing here. I'm estimating what should be the minimum spacing between my rebar. Nothing super. It is 1.4 the bar diameter, or 1.4 aggregate size, or at least 30 millimeter, and this 30 millimeter. Do I have 30 millimeter? Do I have 30 millimeter? Let's check, because remember, there is no super science here. Let me put some dimension. From here to there, how much is that?
Was
450.
it? Yeah,
Thank you,
450.
450. And do we know the cover? Yes, we know the cover.
Yeah.
Do we know the tie diameter? We
Yeah.
will not soon, huh? But anyway, it's a pure geometry problem. So we go ahead and say 450, and I minus 2 cover, and I minus 2 tie diameter, and I minus 3 bars, and I divide by 2, so then I get the spacing, and this spacing must be more than 30 millimeter. So that's one check, okay? And the other check is I'm asking you, when it comes to the tie layout, are we good with only the exterior tie, or do we need to support those bars on the edge? Remember, corner bars are great. They are always supported. No need to do anything for them because this exterior tie will do the job. Really, the question is, what should I do with this? 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 That's the question.
You can only add more ties if your spacing is more than 150. But if it's less
Exactly.
than 150, then you don't need that.
That's exactly what I will do, Jelly. So I'm gonna go right now and I will do it, huh? So here we go. I'm gonna check spacing. So S equal, I will estimate the spacing, which is 450 minus what? Minus 2 multiplied by, let's say 40. It's the cover 40. You guys remember? The cover is 40 or 30. It
It's
is,
40.
huh?
It's 40.
It's 40.
It is 40. Minus 2 times 10 minus 3 times 20, which we have 3 bars. And then finally, this whole thing, you should divide this whole thing by 2, because you can see how many spacing do we have? We have 2
You have
spacing.
2.
Look at the screen.
Yeah,
Any
you
help?
have 2.
Can I get some help?
I got 145.
145. Great. So 145. Do we need to add an independent lateral support for those 4 bars in question, not the corner bars?
No.
No, which means here we go. So we are done when it comes to the bar, the tie layout. We only need a big circular, a big tie that wraps around your bars. We don't need anything extra. If this distance that I just mentioned or estimated a minute ago exceeds 150 mil, in this case, let's say 155, or maybe let's say 160. In this case, no, you need to provide a more support for these bars, okay, which will have to add this diamond tie. Okay, now when it comes to so now we know the shape of the tie. What is the diameter of the tie? I said before there is already condition in the code, but I can tell you all the time will be 10M. So when it comes to the tie diameter, I can tell you all the time will be 10M. How about the spacing, like the spacing of the tie? We have to estimate 4 numbers. Number one is 16 times the smallest bar diameter, which is 20 m. So that's 320. 48 times the tie diameter, which is 480. And then the lateral column dimension, the minimum, is 450. The last one is not applicable because we don't have bundled the bars. So which means we have 320, we have 480, and then we have 450. So the 320 governs, which means I'm going to place ties with this shape here at spacing of 320. Do we see the spacing in this picture here?
No.
No. Where can we see the spacing?
Elevation.
In the section? In elevation.
Near
That's
elevation.
correct. And that's the elevation here. So the elevation here is this dimension between the ties. Simply, this is the spacing, which will be 320 millimeter on center. Last part, we have 4 minutes. So the last part is about splice number. So guys, how we build our column? We finish the floor below, and then we bore this slab here, and we leave those bars hanging until we provide the next cage. Okay? Between the next cage and the starters, we call those our starters, or some people they call them dowel, but they are not dowel. Call them starters. Between the starters and the cage, we must maintain a minimum value. We cannot make those starters very short. We cannot make those starters very short. We have to make sure that we have a minimum value called splice length. Okay? I would, to be honest, I would postpone this to the next class because I need to give you like a little bit of description. So I will just postpone this to the next class. For now, we have 3 minutes. Do you have any question?
No questions from me.
Okay, so here is a request from me. You can see I'm trying to help, but I need also some support from you. Before you come to my class on Monday, you must read today's lecture. Must. Otherwise, because I'm going to give you another example that has a circular column and we're repeating the same thing. So if you read the slides for today, your life will be super easy on Monday. If you don't read the slides, then it is very difficult for you.
You just mean reread the ones that we just did today?
Yes, please. So
Okay.
read the slides quickly, understand what is gamma, why we have so many interaction diagram, what are the factors that we choose one interaction diagram, not the other, all those kind of things. Very simple, very easy, huh?
I can do that.
Okay, sir. Thank you so much. And if you have no question, I will see you tomorrow at 2. Have a wonderful day.
Have a good day.
Thank you, Tahir.
Thank you, sir.